Hi everyone, in this video I'll be showing you the second version of the Baffle grapher, which is a tool used for measuring the baffle profile of any mouthpiece. This is the first version that I made, which works in a totally different way to the second one, and I would recommend watching that video first actually because I'll be referring to some of the graphs that I made on this one. So where the first version of the tool uses these 3D printed plastic shims to actually measure the mouthpiece at a 1:1 scale, the second one uses a digital tip gauge to measure the mouthpiece in a much more accurate way, and that fits in just like this. Instead of the first graph papers, which looked like this and were at a 1:1 scale, the new ones look like this and are much more accurate. So this setup is based on the technique where you can drop the tip down inside the mouthpiece at different points to measure the baffle. You can see me using this method here in my first making a mouthpiece video. The basic version of this technique you can actually try for yourself. You just need to get a little bit of masking tape and then put it right here on the side of the mouthpiece. And just make sure it doesn't go past the plane of the table there. Now this is the kind of tricky part where you need to hold the tip gauge in the exact position that you would use to actually measure the tip opening. And once you do that, you need to make a line that is on the tape here that you'll use to reference against this ruler here. It doesn't matter what number you use, that'll just be your zeroing point to move it back from there. So this is pretty awkward to do, which is why you'll see how this new tool improves this, but if you have it on the tip right there, and maybe I'll choose 40 and just make a line right there. And darken that in a little bit. So basically how the technique works is you would just start by basically putting it where you would measure the tip opening, and that 40 now is lined up with the 0 mark, and then using this ruler you just move it progressively back however many times you want, and then it will read out how far down that tip is plunging into the baffle. So this technique actually works pretty well, and it is very accurate, but there's two main problems with it. First is that it's a little tricky to actually line up the number with this line for every reading. It's not super easy to tell what number you're on. And the other problem is this has to be in the exact center of the mouthpiece side to side, or else you're not going to get an accurate reading. This is just another prototype piece that I printed, and this actually has a flat baffle, so this wouldn't actually matter as much when it moves back and forth. But on a piece that I'll show you again in a minute, like this one, which we'll be using in this video, if you can see there, it actually has a substantial curved baffle side to side. So it's kind of like a compound curve. It's much more complicated, and so if you're moving it side to side, you're going to get a different reading than if it's just in the center. Now, to actually show you how it works, I'll be using the same test mouthpiece from the first Baffle grapher video so we can compare the accuracy. So similar to the first one here, where it had these expanding collets that hold the mouthpiece in place, this one has the expanding collet here also, and this is removable. I'll just show you all the parts of it first. So once you unbolt it like this part is actually free to slide in and out and up and down, which allows for measuring any angle of table and size of mouthpiece basically. This is the tenor size, but I could easily print alto, soprano, whatever else it needs. And then this part here, this actually is basically what replaces the piece of tape on the original technique. So when you slide this in, which actually holds it really secure, there's really no slop in there. It's actually a pretty tight fit, so it doesn't move around. That's how you can much more easily tell what number you're on. It's much more repeatable. So there's actually 3 expanding collets for just the tenor size, but I'll explain that in just a minute. So to actually set it up, you put this bolt through, and then this piece screws on here. And then the mouthpiece just slides on like that. But we want it to be lined up with the flat part here, so to actually do that, you can just put it through here. And then just by squeezing it flat against the bottom flat part of here, it will kind of line itself up. And once it's twisted the right way, you hold it here. Then go ahead and tighten it down. And now that's really secure. I mean, that's not going to move around at all. Then once it's here, you just feed this bolt all the way through again and tighten it down. And because this slot here only goes so far, you actually just push it all the way back and it will bottom out in the same way every time, so you get repeatable results. So you have it slid all the way back and then flat against here. And once it's like that, you just tighten this down. And then that's secure. And this actually does hold it really well. I mean, even putting quite a bit of force on this, you can't really move it side to side, so it's really locked in there. And then this sliding piece here, which actually functions like that blue piece of tape on the original technique, slides back and forth on this rail. And then when you get your tip gauge, so you just set the gauge down in like that. Now move it up to basically where you would read the normal tip opening. So just like that. And now it's a little tricky still, but it works a lot better, where you hold it and then you move this to wherever you want to set your 0 and you tighten it down. In this case, I'll choose 60. So now that that's fixed in place, you can easily tell what number you're on as you move this back. So one other thing that's important to do before you actually start measuring is you can't just zero this against a flat surface like you normally would, because we have to compensate for this thin piece of plastic here. So we actually have to zero it with this attached to it. So you can just basically go like this and then zero it. So the actual whole measuring process I kind of have to do off camera because it's very awkward to hold this and write everything down. But basically, you just start here and then you move it back. And you can see how that end is just following the baffle profile all the way back. And then this guide rail here basically just keeps this perfectly in the center as you travel back. So to explain this new graph paper, it's basically read like this. So the mouthpiece is here, and this line is basically the table. And this is your 0 point. So, and these are all millimeters. So this is actually going to be your tip opening here, or your tip opening will start right around here. And generally, it'll kind of follow this path as the baffle goes down. And then these numbers, these bottom ones are just actual millimeters back from the tip. And then because I'm just choosing 60 as my kind of 0 reference point, that's just the number on the tip gauge that I line up with the actual millimeters. And you can see how those go in reverse order. And then I just write the number down on the top, and then I'll come back when that's all done. Okay, so I've written in all the measurements here now. And then using all those numbers, I can basically just graph out the whole thing. So first I'll just make a dot for each one, and then basically just connect them all to make the line. And then there's my finished graph. So to remind you of the shape of it, you see how there are those two kind of sharp ridges and then the big round one. And that's pretty much what you see here. Those two sharp ridges and then the rounded one. So that's where you get that much more accuracy. You can see how much more blown up that is than 1-to-1 scale. So it's way more accurate. So because of the way this holds this gauge perfectly in the center line of the mouthpiece all the way forwards and backwards, it lets it do something that is actually impossible to do with the just doing it by hand method with the tape, which is that this actually can measure the baffle in 3 dimensions. So basically just by moving the mouthpiece this way, forward or backward, we can have multiple profiles that are next to each other at a known distance, and then that's how we can measure this in 3 dimensions. And to make that happen, that's where these 3 different collets come in. So you can see here how this is the normal centered one, and then this middle one is offset, and this right one is offset by even more. So this is centered, this is offset by 2.5 millimeters, and this is offset from the center by 5 millimeters. So by doing that, now I can do that same measuring process 3 different times, and get 3 profiles all next to each other at known distances, and then I can basically use that information to map out the baffle shape in 3 dimensions. So assuming that the interior mouthpiece shape is mirrored down the center line, which it always should be, then having the center and then 2 offset profiles is more than enough information you need to actually get that side-to-side profile. So here's that mouthpiece I showed a little bit earlier that has that curvature at side to side. Hopefully you can see that. And this is the one that I'll be using for the 3-dimensional measuring. So here it is in the Fusion CAD software, and you can see both the side-to-side curvature and that middle transition, especially when I slice it down the middle like this. So now what I'm going to do to actually really test the accuracy of this tool is from this piece that I've 3D printed from that model, is I'm going to measure it in 3 dimensions, and then use that measurement, use all that data to plug back into Fusion, and then basically rebuild the structure of this baffle next to the original model, and then we can actually visually compare how close they are. So now this piece is all set up for measuring, and I'll have to do that off camera, but I'll come back when the graph is finished. Okay, so given all those data points, here's the graph, and these 3 handwritten rows up here. This bottom one in black is the center line. This middle one in orange is the one that's offset by 2.5 millimeters, and this top one in blue is offset the furthest by 5 millimeters. And the reason why these other ones don't start right at the actual tip opening is basically just due to the arc of the frontal rail here, because, you know, if they're starting at the same 0 point, those ones that are offset actually kind of slip over the edge of the mouthpiece, so you don't really need those readings anyway, and then it's normal from there. So this black line is the center, and then the blue line is the offset by 5 millimeters, and you can see how it starts to deviate more and more as it goes down. And I didn't figure I'd plot the orange just because it's so close to the black, it would just look kind of messy, but I have all the numbers that I can use later. Okay, so this is the 3D model that I've reconstructed from all the tool measurements. Hopefully you can see that the baffle's side-to-side curvature starts out almost flat and then gets more curved as it goes further into the mouthpiece. You can disregard the thickness of the model here. I just set it to 1 millimeter, but that has nothing to do with the measurements that I actually took. And then here's the real test of the baffle measurements, putting it in place next to the original 3D model. As you can see here, it lines up almost perfectly. I did figure that this would be an accurate measurement, but this actually turned out way better than I expected. You can see when it's zoomed in like this, there's only a slight waviness relative to the original, which could be partially due to the unfinished surface of the actual 3D printed mouthpiece. This reconstructed baffle is placed in the same exact way it was measured from the printed model. The relationship and angle to the mouthpiece table and bore was not adjusted at all. And then viewing it from the other end, you can really see how the interior curvature gets more dramatic as it blends into the chamber. This straight-on view really shows the accuracy of the side-to-side curvature, especially near that middle transition angle. And then just a quick look at the 3D model of the tool and how that one adjustment part slides along the rail. Okay, that's going to be it for this video. Thanks for watching.